probability, and I'll be viewing out discrete bivariate random variable with some solved examples in the class as well. We'll move to continuous random variable, thereafter continuous bivariate random variable. We'll move to joint probability function, then conditional probability with solved example. Now, as we all know that probability is a measure of uncertainty, that is when we are not very certain about some event, then that is what probability. So we have different definitions of probability, but in this video we'll be deliberating on the discrete bivariate random variable. When we say bivariate, simply means two or more variables that are random, and we'll be checking out the discrete part. Of course, we can have a discrete distribution and we have a continuous distribution, and one of the axioms that satisfy a discrete random variable DRV with joint probability function is that the probability must be greater than or equals to 0, and the sum of all the probability must be equals to 1. So that is that for that. So we have an example. We have to consider an experiment of tossing 2 dice. So since it is 2 dice, we have our table there, and x1 is the sum of the outcome of the 2 dice. Y is the difference of what? The difference of the outcome. So in this video, in this example, we are asked to find the PMF, that is the probability mass function of the given dice. So since they already told us that x should be the sum of the outcome of the 2 dice and y difference of the 2 dice, you see that when we have 1 minus 1, we have 0. Then we keep on adding. We have 1, we have 2, we have 3, we have 1. We can only have a maximum of 5 for the difference of the outcome. And for the sum of the outcome, we have 1 plus 1, we have 2, then we have 1 plus 2 3, 1 plus 3 4, 1 plus 4 5, 1 plus 5 6, 1 plus 6 7, 2 plus 6 8, 3 plus 6 9, and 6 plus 6 up to what? Up to 12. That can only be the sum of the outcome. And if we are to find the PMF of this table, what we usually do is you take the sum. S is representing the sum of the outcome of 2 dice, and y is representing the difference of the outcome. So coming back to the table, we have 0 to 5 and 2 to 12. So under 1, how many times do we have 1 to appear? That is, how many times do you have the sum of the outcome of the dice? We can have the sum of 2 and the difference of 0. So 1 comma 1 will give us the sum of 2 and the difference of what? 0. Because if you add 1 1, you have 2. If you subtract 1 minus 1, you have 0. And that is the only table that can give us such occasion. So it simply means that the only way we can have a sum of 2 and a difference of 0 is 1. That's 1 over 36. Then moving up to the next one, a sum of 2 and a difference of 1. A sum of 2 and a difference of 1. So if you look at the table very well, you see that there is nothing like a sum of 2 and a difference of 1. Now the scope is, you look at the table horizontally to know which one. You don't need to start looking at the whole table, analyzing the table generally. You look at the table slightly. So you notice that after 1 comma 1, the next one you have is 2 1 and 1 2. The next one we have is 3 1 2 2 1 3. The next one is 4 1 3 2 2 3 1 4. So like that, you look at that pattern down. So using that same pattern, you arrive at the required outcome. So we have it there. So from the table above, what they ask us to do is to find f3, 6. And when we say we have to look for the probability function of 3, 6, it simply means that we take the sum of y less than equals to 3 and y less than equals to 6. So you start from 2 to 6. So you stop at the point at which the question the probability stops, that is 3, 6. So you start from 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 6. Then that's for 2, 6. Then you move to the next phase. That's 3, 0, 3, 1, 3, 2 up to 3, 6. And every other thing apart from that, the remaining part, if you look from the table, you know that those ones are 0. So we are left with 1 over 36 plus what? Plus 2 over 36. Do you understand? So that's 1 over 12. So that is that for example 1. So the second example, we have that we are at a local supermarket, has 3 checkout counters. 2 customers arrive at the counter at different times. So what you should focus on is 2 customers arriving at the counter at different times. So that is our key point. 2 customers arriving at the counter at different times. That should be our focus. So to draw the PMF of this, we have 1 2 3 1 2 3. So, and of course, when we fill up the table, we end at 3 3. So recall for this, the reason why we have over 36 here is because it is 2 dice. So that's 6 raised to the power 2 that's 36. Similarly for this as well, 3 raised to power 2, that's 9. So the overall of this is 9. So y1 is the customer that chooses counter 1, and y2 is the customer that chooses counter 2. So if there is going to be we have 0 1 2, that is, there is a point at which no customers will get to the counter, and there's a point at which one customer will get there, and there's a point at which two customers will get there. Do you understand? So we draw our table, and to find the PMF of this. Now the probability, what we are focusing on is 0 0. If we say 0 0, that's 0, no customer is arriving at counter 1 and no customer is arriving at counter 2. That's 0. That's 0 combination 0, that's 0. And sorry, that's 1, and that's 1/9. You understand? So as a result of since nobody is picked, it simply means that there must be at least one person that will arrive at the counter. Do you understand? Now the second one is no customer arrive at counter 1 and one customer arrive at counter 2. So what we are after is actually two customers, the arrival of two customers. We are not after be it 1 or 2. So far one customer arrives, it simply means that that's two customer, that's 2/9. So far one of the customer arrive, whether it is customer that arrives at counter 1 or customer that arrives at counter 2. So far that's what we have after. So far one customer arrives, it simply means that will be what? That will be 2/9. And similarly the other one, we have no customer in y1 and two customers in y2. So no customer is arriving at the other part. So that is not our aim. Our aim is that at least one customer will arrive at the counter. So you see that as well is what is 1/9. So we move to the other one too. You see that the other one, 1,0 as well will be 2/9, because at least one customer arrived at this part, so we have 2/9. Similarly 1,1, one customer arrives, that's 2/9. So the other one customer arriving at C1 and the other customer arriving at 2, that is not possible, so we have that to be 0. So for the last part, two customer and no customer at counter 2, that is 1/9. And of course the rest 2 1 and 2 2 is not possible. So that is our PMF. And to check if this is a probability mass function, you have to add all the elements together and it must give you 1. So that's 1 2 3 4 5 6 7 8 9. That's 9/9. That will give us what? That is 1. So similarly we are asked to look for f0, 1. F0, 1, you have to start from 0, 0 and you stop at 0, 1, and we have 1/3. So these are questions on discrete random variable. So we move to the continuous random variable. The continuous random variable simply deals with integral, and disjoint interval. So those ones, once we have a required integral, they must obey the rules of probability. So f of x must be greater than 0 and the integral of -infinity to infinity must be equals to 1. So we have an example here. Given f of x to be cy squared, you are asked to look for the value of c, and of course since we know that all probability distribution must be equals to 1, we make c the subject of the formula and we apply our boundary, and we have c to be 3/8. Then we insert 3/8 back to the initial question. Then we compute y greater than equals to 1 and y less than equals to 2, so as the boundary. So we have our final answer to be 7/8. Now we move to cumulative density function. Cumulative density function simply means, of course, know the difference between the big F and the small f. When you take the inverse of this, inverse of x, you have small f of y, that is f of x, probability max function. Then this other one is what is a PDF, probability density function. So we have continuous bivariate random variable. So we have that let x and y be a continuous random variable with joint distribution function. So we have joint for continuous random variable as well, that is bivariate random variable. So if we have fx, y and we have two different distributions, we take the integrals respectively and we have some of these rules to be here. So we have an example. We have that fx, y to be 6/5, that, and we are asked to look for s less than greater than y. So s less than greater than y simply means that 0 to y, 0 to 1 and 0 to y of that function. And when we solve that function and when we solve the integral and put our respective values, we have 5/12. So similarly, we are asked to look for f1 over 2, 3 over 4. You must be very careful when it comes to the boundary. When it comes to the boundary, you must be very careful in locating your boundary. You might need a graphical representation for that aspect. So, but in cases whereby you are asked to look for f1, 2, 3 over 4, what you just do is to insert your values, your boundaries from 0 to the first one, from 0 to x, y respectively. So that is that for that. So conditional probability, this is the more advanced form of the normal conditional probability. That's P intersection B over P of B. That's conditional probability. So similarly, for a marginal probability function, MPF, for a marginal probability function, we have that y2 must have been given for y1 to exist. That is what conditional probability simply means. That is, a function is dependent on another function, or a variable is dependent on another variable. So that is it. So we have that, the formula as that. So similarly for p y2 comma y1, you can see the formula as well. So now we have an example. We have a table. This table is already given, and what they ask us to look for is py1 comma 1. It simply means that 1 is representing y2, so it means that y2 is already given. So what we look for is py1 comma 1. So since y2 is already given, what we look for is the parameters respectively. To look for p2 comma 1, we have to start from p, where you must stop is 2 comma 1. So but before 2 comma 1, you have to start from 0 comma 1, 1 comma 1, then 2 comma 1. The 1 remains a constant because it is already given. It is given in the question. So what changes is 0, 1 and 2. And of course, checking through the table, we have 0, 1, 1, 1, 2, 1. So when you add everything, you have 8 over 15. That is for p2 comma 1. Then py comma 1, py1 comma 1. Now if you look at the table, the only situation whereby we can have a number and 1 is when we have 0, 0 and 1. That is 0 and 1. And what do we have under 0 and 1? What we have under 0 and 1, that is y1 to be 0 and y2 to be 1. That is the only case we can have. That is 2 over 15. And if we check the 2 over the table, 0, 1 is 2 over 15, and we have that. Then we apply our formula back. Then we have our final answer to be what? 2 over 8. So similarly, we have y2 to be 2. In this case, they give us all the values. They give us y2, y1 already. So what we do is, going back to the table, 1 comma 2 is 0, and 1 comma, of course, since the numerator is already 0, everything becomes 0, and that is the representation for that. Now if y1 and y2 are jointly continuous random variable, now the only situation, that is y1 and y2 can only be jointly continuous random variable if the both of them is greater than 0. Do you understand? Or you take their integrals, and the integrals become what? Become 1. And of course, if you take fy1 comma y2 over f2y2 dy1, taking f2 comma f2y2 outside, because it does not become a constant. And when you take a function of y1 y2, what you do is you are integrating it with respect to y1. So far the function is starting with y1. What you are doing is you are integrating it with y1. If it is starting with y2, you are integrating it with y2. Do you understand? So when you insert the respective formula, what I'm saying is that f of 2y2 will give us the integral of minus infinity to infinity fy1 comma y2 dy1. So when you insert that, you have that to be 1, and this has proved this to be what? A PDF. Okay, so we have the other part. We have the cumulative conditional probability. When I say cumulative conditional probability, it simply means that we'll be taking the integral of the conditional probability. It is no longer conditional, but it is now a cumulative conditional probability, and of course it is continuous. So what we do is to take the integral. So similarly, if it is y2 comma y1, what will be down is f1 y1, and we will be integrating with respect to what? Y2, because it is starting with y2. But if it is starting with y1, we integrate with respect to y1 as well. So we have some examples here. Let y1 and y2 be continuous random variable joint density function. So we have that 0x way. We have to look for f1 y1. f1 y1 simply means that we are integrating with respect to y2. This function, recall, they gave us the boundary. They gave us the boundary of y1 to be 0 to 2y1. You can see clearly from the boundary 0 to 2y1. Then when you integrate, that will be 12y1 dy2. The function, what they ask us to do is the function and y1. The function and y1. The function is 12y1. Do you understand? And if anywhere you see y1, we have it to be dy2. If it is y2, it will be dy1. So just take note of that. So when you integrate, we have 24y1 squared. So similarly, we write our function. Note that whenever you finish solving the distribution, the function, you should always represent it in the pattern of red, of the red ink. So you solve for f2y2 as well. So solving for f2y2, we have the required parameters. We have our answer to be that. Solving for f2y2, that is the representation. Now this is the third one, is a conditional probability, fy1 given y2. So we already know what y1 comma y2 is from the above. So when you insert them back here, we have our answer to be 1 over 2 y1. Then fy2 comma y1, we already know what y1 comma y2 and f2y2 is. So that's that. So on simplifying, we have hy1 over that. So now the function, you notice that there's a difference between the big F and the small f. The big F warrants you taking the integral, while the small f simply means you are just taking the conditional distribution like that. But whenever you see a big F, it simply means that you are taking the integral, or you are taking the summation, be it given the type of distribution it is. So we have, when you integrate this, now every other thing, 8y1 squared, when you integrate this, we have we are integrating with respect to y1, so every other thing becomes a constant. That is 1 over y2 squared becomes what? It becomes a constant. So we have our answer to be that. So similarly for y2 y1, our boundary for this will move from 0 to y2. You can see the first one was 0 to y1, so we have y2 over 2 y1. So we have an example. They gave us y1 less than greater than 1 over 2 and y2 to be equals to 1 over 2. So, and of course, so 0 to y1, the integral of this, that's what they want us to do, is to take the integral of what we already have in the previous answer, the integral of 4y1 squared over 1 minus y2 squared. So when you take the integral of that and you insert the necessary boundary of 0 to 1 over 2, we have our final answer to be 8 over 3. Then the next one, we have joint density function. Let y1 and y2 have the joint density function, these blah blah blah. Then, and of course, we have to be very careful. They ask us to find y1 plus y2 less than 1 and y1 less than y2. We can't have an addition sign unless we make one of these the subject of the formula and represent it in a conditional probability form. Do you understand? So when we make y2 the subject of the formula, we have it y2 less than 1 over 1 minus y1 given y1 less than 1 over 2. And recall that probability of A intersection A given B is A intersection B over P of B. And of course we have it to be what? That we have our representation to be that. Now they already said that y1 plus y2 is less than equals to 1. If y1 plus y2 is less than equals to 1, it simply means that is either y1 is 0 or y2 is 1, or y1 is 1 and y2 is 0. These are the only conditions that we give that y1 plus y2 must be equals to 1, because the condition is less than or equals to. So we are considering y1 plus y2 to be equals to 1. So the only condition for this to happen is that is either one of them is 0 or one of them is what? Is 1. So that is it. So let's go. So we have our boundary. Coming back to this, we have our boundary. Our boundary will be from 0 to 1 over 2. From y1 less than 1 over 2. That's for y1. And the other one will be from 1 over 2 to 1 minus y1. You know that is y2 now, because we already said y2 is less than equals to 1 minus y1. So that will be from 1 over 2 to that. And when we insert our PDF, that's 2y1. So we integrate them respectively. So that's dy2 dy1. Then since it is a joint density function, we are joining density functions together. We have, it will also be from plus 0 to 1 over 2. I would have loved to sketch this graph, but it will also be from 0 to 1 over 2, 0 to 1 over 2. Then we take the distribution 2y1 dy2, and when we solve the integrals respectively, we have, you can check them out, just write them out and see. We have our final answer to be 1 over 6. That is for the first part. to be 1 over 6. And for the second part, y1 less than 1 over 2, what we just do for this is take the integral 0 to 1 over 2, that's 0 to half. It can't be greater than 1. So it must be between the range of 0 and 1. So it's either moving from 0 to 1 or 0 to half or 0 to 1. When y 0.5 1 over 2 is representing the midpoint of 0 and 1. Do you understand? So that's just the graphical sketching. So that is it. So when you solve the integral, that's 1 over 4. Now this other part, recall that y2 less than 1 minus y1 intersection y1 less than 1 over 2 is 1 over 6. So when you apply the formula of the conditional probability, we have our final answer to be 2 over 3. So that is all for this video. So we've done cumulative conditional probability, the definition, the conditional probability, the joint probability function, the cumulative continuous random variable, the joint distribution function, and the likes. So you should know the difference between PDF, PMF, and probability max function, probability